In this video, I'm going to show you the image of why we must apply good layout matching with the same unit size and dummy devices. Before going to the good layout matching exercise, let's see an output transconductance amplifier OTA along with its biasing circuitry. From the circuit images, the supply independent bias current with the resistance RS is sending the current IP to the OTA bias. And then, obviously, all the mirrors are performed through the VCSN, VCSN, and VPCS. As we discussed in the white current mirror video, those current source devices must match well between the bias and the OTA. Let's look at the device size of the current source between the OTA and its bias closely. The most obvious one is the channel length is all 1 micrometer at the PMOS and NMOS current source. Therefore, the matching should be good. For the channel width of the NMOS, the total width is 2 micrometer at the bias and 8 micrometer at the OTA. On the other hand, for the channel width of the PMOS, the total width is 8 micrometer at the bias and 32 micrometer at the OTA tail current and 16 micrometer OTA output current source. Therefore, the ratio of the device is 1:4 at the NMOS and is 1:4:2 at the PMOS. If we draw the tail current I and the PMOS current source a half I on each side from the source VDD-HV, then both NMOS current source would have a sink current I to the ground respectively. The OTA designer seems to have a good design images here, does it? But do you see the unit size of the NMOS isn't the same even though the unit size of the PMOS is the same? Do you see any total width issue from the current equation here? Probably not, since the ratio of the total width is correct, no matter what the unit width. Could you please think about the unit size layout images for 5 seconds? Bingo! If you look at the layout image of both NMOS at the bias block and OTA one more time, what do you see? Exactly, their looking is not exactly the same. If they are not exactly the same, what happens? The first one could be easy to guess. Could you please think about the stress images for 5 seconds? Correct. In a transistor fabrication, the shallow stretch isolation may have a stress effect, which is due to the thermal expansion of materials. Therefore, the silicon mobility and the threshold voltage VTH will vary between each devices. Hopefully, the stress can be modeled, and the foundry like TSMC has been included in the SPICE model with the parameters called SA, SB, and SC. If you look at the post-layout iteration netlist, you should see those parameters will be much different if there's a big layout mismatch. Furthermore, if you run the SPICE simulation, you must notify the ID set, GM, and VTH are much different if all the SA, SB, and SC are much different between the devices. Again, if layout image of the current mirror between the OTA and bias are not exactly the same, what else could be wrong? Think about the well image from the CMOS fabrication for 5 seconds. Right, the well will result in a dopant gradient, and the doping at different distance to the well will be different. For example, the well proximity effect WP will cause the transistor close to the well edge to have a difference in the threshold voltage and also current compared to the devices far away from the well edge. Again, hopefully the WP can be modeled and the foundry like TSMC has been included in the SPICE model with the parameters called SCA, SCB, and SCC. Similar to the stress effect, you could check either the post-layout iteration netlist or the simulation current and threshold voltage if there's a big difference for poor layout matching. After we know how the layout mismatch in the unit width may have a big mismatch on the current mismatch, could you please think about what could cause the issue in the OTA and its bias for 5 seconds? Great. We could start from the threshold voltage image, VTH easy. If the bias current unit has a lower threshold voltage or higher doping, the bias current will generate a smaller diode voltage VCSN to the OTA. Unfortunately, the OTA unit may have a higher threshold voltage or lower doping to generate a smaller current near half IN or less. On the other hand, the PMOS may have a good matching with the total tail current equals to IP or IN. Then what happens? Could you please think about the Kirchhoff current law KCL image from the Microelectronics 101 for 5 seconds? Correct. Since IP equals IN, then both the IP2 and IP3 must be 0. So the output voltage of the OTA would be near 0 due to the high impedance at the top branch. Again, if the layout mismatch was so serious, what can we do better? Think about the exact image for 5 seconds. Bingo! You probably hear I emphasize the exactly the same several times since it's the simple key to making good matching. What was the first thing to do? Right, we must make every device has exactly the same unit width and length. How about now? Still not enough, right? Could you please recall the stress or WP images for 5 seconds? Correct. We need to keep all the stress and WP exactly the same for all the transistors. Therefore, we could put non-functional transistors outside of those main functional transistors, such that all the mirroring transistors would match well in terms of the stress and WP. That's why the dummy devices in the layout are so critical and helpful. Here are the summarized images of why we must apply a good layout matching the same unit size and dummy devices. We start with an OTA and its bias images in the design exercise. All the mirroring ratios in the total channel width and length are perfectly matched in the schematic. So, looks like a great design. But we saw the layout between the OTA and its bias were not exactly the same in the almost mirroring. Those layout mismatch will cause lots of mismatch in the device mobility, transconductance GM, threshold voltage VTH, and current due to the stress effect SA, SB, SC, and WP, SCA, SCB, and CC. If we went back to the OTA and its bias in simulation, we could see the bias mirror voltage could be too low to generate the OTA's output almost current a lot due to the big VTH mismatch. Lower are the bias, but bigger are the OTA. Therefore, the OTA output will stay low due to the zero current at the output branch on the top. To resolve the matching issue, we must apply exactly the same unit size transistor in length and width. Furthermore, necessary dummy devices are a must to add around those critical mirroring devices. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.